Now, the binomial theorem that you learn in algebra requires that you have positive integers as your powers. I know I said it's n, but if you look at the theorem, it's really p. It's that p has to be a positive integer. But that is not true, as we discover. So that was true in algebra, but it is no longer true in calculus. Matter of fact, it never was true, but we just kind of lied to students back then. Of course, the only exception to that is except 0. Although you wouldn't need this theorem for 0 anyway. All right, so for any real numbers, any power, p not equal to 0, the Taylor series for that function would be equal to the combination p, choose k, x to the k, which would be 1 plus, and you can see how it works, right? So you take p times p minus 1 times p minus 2 all the way down to p minus k plus 1, and then you multiply by x to the k over k factorial. So for example, it's 1 for the first one, and then p times x plus, then p, and then subtract 1, right? So now you've got 2 pieces, and so it's 2 factorial to the squared. Now do 3 pieces, right? P minus 1, p minus 2. So that's divided by 3 factorial times x cubed, and so on. That series converges for x less than 1. The absolute value of x is less than 1. And possibly at the endpoints, it depends on what your power is, so you have to check those. So if you were interested in that. Of course, as we've seen in a previous example, if p is a non-negative integer, if p is positive, then the series is going to terminate and result in a polynomial of degree p. We saw that with the Taylor series expansion of a polynomial a couple examples ago. So that makes it actually quite simple if p is a non-negative integer. Just a reminder, we saw something like that in example 4 here, when we had a polynomial and it ended up not being an infinite series. So we could say, note, see example 4, right? Because if you have a polynomial with a non-negative power, then it'll work out fine, and you'll have a terminating series that doesn't go to infinity. Now let's use this lovely theorem and consider the function f of x equals 9 minus x, which we all know is 9 minus x to the 1/2 power. A power, interesting. Okay, so I want to find the first 4 terms of the binomial series for that function centered at 0. Okay, so I'm going to develop a series for f of x equals 9 minus x to the 1/2. Now this doesn't actually fit into the form. So if you look at the form up here for the theorem, it has to be 1 plus x to a power. So I'm actually going to have to change this a little bit. So I'm going to start by factoring a 9 out of this. So if I took a 9 out, that would leave me 1 minus x over 9 to the 1/2. Or if you like, square root. And the square root of 9 is 3. So that's 3 times 1. And since it has a plus in there, I'm going to write plus, and then it's negative x over 9 to the 1/2. All right, so I've got my A, my B, and my C, or my P. A for me is 1. B is negative x over 9. Excuse me, my P, there it is 1/2. So for that Taylor series, that would be equal to, oh, there's a 3 in front, so I'll just put a 3 in front of the whole thing, right? So that's that bit. And then it's from k equals 0 to infinity. I'm going to use my power, which is 1/2. I'm going to choose k, and then I'm going to have x, but x for me isn't as clear cut as it was in the theorem up above. So in the theorem up above, they're using x, but in my problem, I'm going to use negative x over 9 to the k. So it has to be basically in the same form if you're going to use this theorem. In particular, you need a 1 in front. So I made it so there was 1 in front, and then it's okay if there's a little function of x, and that's what I used right there. So negative x over 9. So this is the Taylor series, or the binomial series, excuse me. Now they want us to write out the first 4 terms. Oh, and it's centered at 0, so, well, it will be in a second. All right, so I want the first 4 terms. So that's 3 out in front of the whole thing. And then I want to have one, well, it's 1/2 choose 0. And then negative x over 9 to the 0 power. There, it was a little lopsided. All right, then I'm going to have 1/2 choose 1, and then negative x over 9 to the 1, plus, so that's 1, 2, I need 2 more. So 1/2 choose 2, and then I have negative x over 9 squared, and then 1/2 choose 3, and then negative x over 9 cubed. So the difficult part is actually going to be these, well, actually, this one's not hard. It's these two combinations right here and right here that are going to be a little bit tricky. All right, so 3, anything choose 0 is 1. So this whole thing is going to be 1 because that's 1 and that's 1. So 3 times, so it's 1 plus, all right, this bit right here is a 1/2, right? A 1/2 choose 1 is a 1/2. And then times negative x over 9. And then a 1/2 choose 2. Let me write that one out. So it's going to be a 1/2 times a 1/2 minus 1 over 2 factorial. I'm using this property right here, right? I just know how this will work out. So it'll be a 1/2, that's my power, a 1/2 minus 1 over 2 factorial. So that'll be that one. I'm not really writing out all the formula with the whole subtraction and all of that. I'm kind of cutting out the middleman that we saw on the previous page where you keep subtracting 1 and canceling. And then it's times negative x over 9 squared. Then plus. And then the 1/2 choose 3 is right here. So I do a 1/2 minus 1, and a 1/2 minus 2. So it's a 1/2 minus 1, and a 1/2 minus 2, all over 3 factorial. And then that'll be times negative x over 9 cubed. Now technically this keeps going, so I'll just put ... there, right? We're just writing out the first 4 terms of it, but there you have it. All right, so then that would be 3 take away, let's see, 3 goes into that, 9 goes in 3, so 3 times 2 is 6, so negative 6 over, or excuse me, negative x over 6 plus, using Desmos, I can see that a 1/2 times a 1/2 minus 1 over 2 factorial is negative 1/8. If I put a 3 times in front and then a 1/9 in back, oh, 1/9 squared, so 1 over 81, like that, I can see that it's going to be 216. So be it. Right here. So that means that this part right here, with the 81 right there and the 3 out in front, is going to be x squared over 216. It'll be negative because there's a negative right here and this is positive. So because that's negative, it'll actually be minus x squared over 216. And then, let's see here, plus, and then I have to do it all again for that next term. And there you can see it in Desmos. So 3 times, because there's the 3 out in front, a 1/2 times a 1/2 minus 1, a 1/2 minus 2 over 3 factorial, all times 1 over negative 9 to the 3rd would be negative 1 over 3888. And that'd be x cubed. So again, I have a plus, but I don't need it. I want a subtraction. So negative x cubed over 3888. And technically this would go on, I'm going to guess it would go on negative, but who knows? There we have it. So this is f of x. So this is the square root of 9 minus x is equal to this series, continuing on. But we've got the first 4 terms as asked for. So now we want to approximate square root of 8.85 to 3 decimal places, assuming that the series for f converges to f. So this series that we just invented here, assuming that that converges within that interval of convergence. All right, so I'm going to let g of x be this piece. So we'll let, for part B, we'll let g of x, which is going to be what we're going to use to make this approximation, be 3 minus x over 6 minus x squared over 216 minus x cubed over 3888. And we're going to stop right there. We're not going to keep going with this dot, dot, dot. So that's the first 4 terms. So if I want the square root of 8.85, I'll put that over here. The square root of 8.85 is equal to the square root of 9 minus 0.15, right? So 9 minus 0.15 will get you 0.85. So that means that x is equal to 0.15, which is within the interval of convergence that we were given of -1 to 1. So this is great. So what I really want to find is g of that x value, which is 0.15. Well, that's what Desmos is for, right? So I've got my approximating function, right? So square root of 9 minus x is really this series that goes on to infinity, right? And then it's for the interval that they gave us, for -1 to 1. So it says in part B, just assume from -1 to 1. So I'll just say that. Right? So then I'm taking the first 4 terms only, which won't be as good because I don't have all the rest of these infinitely many terms. And I'm going to figure out, well, what happens if I put 0.15 in there? 9 minus 0.15 would be 8.85. So let's not use the whole thing. Let's just use the first 4 terms. And that is what Desmos will do. There, I find it easier just to name the function. And then say I want g of 0.15. And there we have it, 2.974894, yada, yada, yada. It might be interesting to note what the square root of 8.85 is, as far as Desmos is concerned. And you can see where they're losing difference is there in those last few decimal places. So it has 5613 there. And that difference between what we thought it would be and what it actually was is the remainder that we were talking about for the remainder theorem. The difference in these two is equal to the remainder, also known as the error, because this is what it actually is, well, more or less, and this is what an estimate is.